we have properties of logarithms, and the first one is if you have a log with any base, and this one is a 1, we know that's going to be 0. And that's because any number raised to the 0 power is always going to be 1. The next property, log a of a is going to be equal to 1, because we know that a to the first power is always going to be that same number. The exponent of 1 doesn't change anything of your base. If we have log a of a to the x power, this is going to be equal to x, because we know that a log of a cancels out and you're only left with x. And if you have log of base a of x, and that's equal to exactly log a of y, then we know that y and x are going to be equal to each other. You're going to find the inverse of the function. And the first thing that we're going to do in this case is we're going to replace the f of x with y, and we're going to make that equal to 12x. And whenever we're doing inverses, we're going to swap the x and the y. So we're going to change locations. What we're going to try to do is make sure that the exponent is brought down. And to do that, we need to put log 12. We know log 12 of 12 from the properties that we saw is going to be 1. So we end up with log 12 x is equal to y, because this cancels out. And this is going to be your inverse function. So we're going to say that f inverse of x is equal to log 12 of x. To find the inverse of this one, we are going to again start with replacing the f of x with y, and we put log base 9 of x, and then we're going to swap the x and the y, and we are going to solve for y. Now, using the properties that we have a log 9. So that means that we need to put a base that will cancel that log 9, and that base is going to be 9. So we put a 9 right there. This portion cancels out. So we end up with 9x is equal to y. And then we can rewrite it as f inverse of x is equal to 9 to the x. We know that when we have a logarithm with no base, we automatically know that that's going to be a base of 10. But we also have logarithms with base of e, like in this case. And we actually write it as ln. So instead of writing log base e, we just write it as ln. And right now we're going to compute ln of e. So put that in your calculator. Ln of e is 1, just like log base 10 of 10 is 1. We're going to use our calculator to evaluate the functions. So that means that we are just going to input in the calculator log 5. When we put log 5 and we press enter, we get that log 5 is equal to 0.6989, and there's multiple decimals after that. For the most part, we are only just going to round to 3 decimal places. And then we're going to put ln e And again, like we saw before, you get 1. Now the answer does change based on the logarithm. Let's try if we put ln of 5. You're going to press natural log, put 5, press enter, and that one actually gives you 1.609. So based on your base, you're going to be getting different answers. Anytime that you get something in the form that says evaluate, that means that you're going to be looking for a precise number and you're going to be using a calculator unless you can simplify. The properties of natural log are going to be similar to the properties of logarithms. So if we have ln of 1, that is going to be equal to 0, because if we have e to the 0 power, that's going to be 1. If we have ln of e, as we tested out earlier, that's going to be equal to 1, because e to the first power gives me e. Ln of e to the x is going to just be x. And again, this is because the ln and the e cancel each other out. And if you have ln of x is equal to ln of y, we know that x and y are going to be equal to each other. Anytime do you have positive b, m, or n, they could be fractions. They could be rational numbers. B is not equal to 1, so we cannot have 1 as a base. We can say that anytime that you're multiplying two things right there, you can rewrite them. You're going to keep the base on both parts, but these two things that you're multiplying, you can put it as you're adding the items. We can say log b plus log b of n. The quotient property is similar to the product property. So once again, as long as you have positive numbers and b is not 1, anytime that you have something that you're dividing, you can rewrite it as a subtraction. We are able to use this in order to try to simplify some of the results, try to simplify that expression. For example, if you are given log 4 of 18 minus log 4 3. Anytime that you have something like that, you use this property to change it up, and we're going to say that this is going to be log base 4 of 18 over 3. And we know that this is going to be log 4 of 6. The power property tells you that anytime that you have a number as your exponent, you're going to put it in the front of the logarithm. If you had something like log 4 3 to the 4th power, you can rewrite that as 4 log 4 3. Or if you had log 5 to the 7th, that is the same thing as saying 7 log 5 of 5, and we know that log 5 of 5 is equal to 1, so we are going to say that this is 7 times 1, which is 7. You use the properties to try to simplify it and make sense of the problems, because you need to be able to manipulate logarithms and exponential functions as much as you can. Let's say that we have a logarithm base 2 of 3, and this is approximately 1.585. And we also have log base 2 of 7, and that's 2.807. Now, to evaluate the logarithm, you don't need to try to put it in the calculator, because with the information that we have, we can actually do basic computation. So in this case, it's telling me that log base 2 of 3 over 7. So the only thing that we're going to do in this case is we're going to split it, and we're going to say log base 2 of 3 minus log base 2 of 7. We already have the numbers up here, so the only thing that we're going to do is 1.585 minus 2.807, and this will be equal to negative 1.222. We can do the same thing for part B. Now, in this case, we have log base 2 of 21, but we know that log base 2 of 21 can be written as 3 times 7. So what we're going to do in this case is we're going to write it as log base 2 of 3 plus log base 2 of 7. So that means that we're just going to be adding the numbers. So we're going to have 1.585 plus 2.807. So we just need to add these numbers. And this is going to give us 4.392. For part C, we can do it in two different ways. You can do it as log base 2 of 7 to the second power, or you could technically do it as log base 2 7 times 7. They will both give you the same answer, but in this case I want to stick with the easier property, so I want to put 2 log 2 of 7, and we know that that's going to be equal to 2 times 2.807. That gives you 5.614. So when we have to expand, we're going to be dealing with parts at a time. You don't want to do everything in one motion because you're going to make a mistake. So what we're going to do in the first one is we're going to split it in the things that you are multiplying. So you have the 5 and the x to the 7th power, and we know that you're multiplying those. So I'm going to put ln of 5 plus ln x to the 7th power, and then we're also adding the part that you're dividing, and we know that with the property we're going to be subtracting, so we put ln y. Now we have an exponent and we need to get rid of that exponent, so we're going to put ln 5 plus 7 ln x minus ln y. And now that's the way that you expand the whole expression. If we need to condense, again, you're going to be looking at the operations. So in this case, we have a log, and then we have 2. The fact that we're adding this 2 means that we're going to be multiplying. So we have 9 times 2 to the 3rd power, because this is going to be your exponent. And because we are subtracting using the property, we're going to be dividing by 3. Now, we're not fully done in this problem. because we have 9 divided by 3. So we can actually simplify this to log 3 times 2 to the third power. The change of base formula is very important because in a traditional calculator, you're not able to put different bases other than base 10 and the natural log. So if you need to compute numbers with different bases, in this case you have log base c of a, you're able to change that by putting log base b of a over log base b of c. Now you need to make sure that your b is going to be something that it's acceptable to the calculator. So for example, if you had log base 3 of 7, we are going to replace this with a natural log. So we can say ln 7 over ln 3. Because we can actually just compute that in the calculator. We can put ln 7 over ln 3. Now, you don't want to put something like log base 4 of 7 divided by log base 4 of 3, because even though that will give you the correct answer, your regular calculator won't be able to compute it. So now we're stuck in the same issue. So this is not ideal. So once again, the best use for change of base is going to be your base 10 and your base e. And I'm giving you 2 examples of how they will look like when you put them in the calculator. So log a divided by log c and ln a divided by ln c. We're going to change the base of this one, and it's telling you to use natural logarithm. So we're going to use ln. So we know that log 6 24 is going to be equal to, the common base is going to be e. So we have ln of 24 divided by ln of 6. To input it, we're going to put ln 24 divided by ln of 6. You need to make sure that you close parentheses to make sure that you get the right answer. And this is going to be equal to 1.77. And again, we're going to round to the third decimal place. If you get in the problem that it tells you the common logarithm or the common base, that means that you're going to just use base 10 instead of the natural log. So now we're going to combine everything from the lesson to make sure that we're able to solve this equation. So we're going to start by getting rid of the 2 to make sure that we can bring down the x. So we're going to put log 2 of 2x, and that's going to be equal to log 2 of 7. So this cancels and you're left with x is equal to log 2 7. Now to evaluate this using your calculator, we're going to do a change of base, and I'm going to use a common base. So I'm going to put log 7 over log 2. So we're just going to do a change of base, and we're just going to input that in the calculator. Our answer is going to be 2.807. Some of the problems are going to be more complicated and they're going to require you to think outside the box, and this is an example of that one. So the first thing that we need to keep in mind is that you have x's on both sides in this problem. But what we need to try to do is make sure that we have the same base. So right here we have 100, and then right here we have a 1 over 10. The best way that we can solve this problem is by making sure that they both have a base of 10. And to do that, we're going to rewrite this as 10 to the second power to the x. And we can rewrite 1 over 10 as 10 to the negative 1 x minus 3. Using the properties of exponents, we know that whenever you have an exponent raised to an exponent, you just need to multiply them. So we have 10 to the 2x is equal to 10 minus x plus 3. Now you do log on both sides, just with your common base. This will cancel, and you have 2x is equal to negative x plus 3. We add x to both sides, and we get 3x is equal to 3. We divide by 3, x is equal to 1. For this problem, we have something similar. We want to make sure that we have the same bases, and the first one is 512, and we know that we can rewrite that with a base of 8, and then 1/8 you can write it as a base of 8. So we are going to rewrite this as 8 to the third power raised to the 5x minus 1, and that's going to be equal to 8 to the negative 1 minus 4 minus x. You use the same property, so you have 8 to the 15th x minus 3 is equal to 8 to the 4th plus x. You're going to do log base 8 on both sides. They cancel. You have 15x minus 3 is equal to 4 plus x. So we're going to subtract x, and you get 14x minus 3 is equal to 4 plus 3 plus 3. 14x is equal to 7. So we know that x is going to be equal to 1/2. So in this one, we're going to be paying attention to things with logarithms, and in this case, we have a natural log. So to get rid of that natural log, we need to make sure that we're using e. So we're going to put e right here and e right here. This cancels, and we're left with 4x minus 7 is equal to x plus 5. I'm going to subtract x from both sides, and now I'm going to also add 7 to both sides. Just doing everything one step. This cancels, and we have 3x is equal to 12. Divide by 3, x is equal to 4. Now we're going to solve this logarithm. And the first thing that we need to do is get rid of that 2. So to get rid of the log 2, we're going to just put 2 and 2 as your base. This cancels, and we're left with 5x minus 17 is equal to 2 to the third power. But 2 to the third power is going to be 8. And then we're going to add 17 to both sides. So that's 5x is equal to 25. Now we divide by 5. So x is equal to 5. So for this one, we have multiple logarithms, and in this case we have the same base, which is going to be 10, and we're going to use the properties of logarithms first before we can solve it. So we're going to say log of 2x times x minus 5 is equal to 2. Now I'm going to get rid of the log by putting a base of 10. This cancels, so we're left with 2x times x minus 5 is equal to 100. We're going to distribute the 2x, so we have 2x squared minus 10x, and that's going to equal to 100. Because we don't have a straightforward answer, we're going to have to solve this using any method from quadratic functions. So I'm going to subtract 100 from both sides. 2x to the second minus 10x minus 100 is equal to 0. And we just need to solve for that portion. You can divide everything by 2. So we have x squared minus 5x minus 50 is equal to 0. You can factor this by finding two numbers that when you multiply them gives you negative 50, but when you add them gives you 5, and that's just going to be 10 and 5. So we have x minus 10, x plus 5, and that's equal to 0. So we have x minus 10 is equal to 0, x plus 5 is equal to 0. So x is equal to 10, and x is also equal to negative 5. Whenever you're dealing with logarithms, we need to be careful with whatever is inside the parentheses. That number must always be greater than 0. So you cannot have a negative number there. So if you were to use the first answer that we got, negative 5, if you were to put negative 5 right here and then negative 5 right here, the calculator will give you an error. But if you plug in 10, you actually get a number. So we know that negative 5 cannot be an answer because we cannot compute negative logarithms, but it can compute positive ones. So if you put in 10, you will get that expression will equal to 2.